Thank you. I'd like to begin by thanking the organizers for this opportunity to be here and talk in front of old friends and maybe make some new friends. This is work largely done by 3 students. One of them, Anup Raj, is a PhD student in IIT Bombay. The other, Sabyasachi Chaudhary, is Trideep's student, and Jay has just started working with me. And it sort of splits naturally into 2 parts. One is the bipartite problem and one is the non-bipartite. So I've sort of kept them separate. It's still not written up, so this is all notional. But it relies very importantly on some background work, previous collaborations with my former student Geet Rakala and some. So let me begin with a very brief primer on dimer models on bipartite lattices, on regular bipartite lattices, which means the same coordination number everywhere. We expect such models, if they are fully packed, to be critical. And what I mean by critical is some sort of power law correlations for the dimers. And the basic idea behind this is that this expectation is that you can define a divergence-free polarization field on the links of the lattice. You just say that this is a vector that lives on the links, and this is the unit vector pointing from the A site to the B site, and this is the scalar that goes in front of it. So if there's a dimer present, NAB is 1, then you have an arrow going from A to B. If NAB is 0, you have a smaller arrow going from B to A. And this is just rigged up so that the full packing constraint becomes a constraint on the polarization field, saying that the divergence is 0. So now you can make contact with sort of the behavior of polarization fields in ferroelectrics. It's an old idea, but there's a more recent review which is really readable and which is where I learned everything from, by Chris Henley. And so then you solve for this constraint by saying P is curl of A and write an effective action down. And then dimer-dimer correlations are correlations of this curl of A. That's the idea. And because of this, one generally expects that the dimer-dimer correlators are dipolar in form, because after all, it's the polarization field which is divergence-free. It's a dipole. So you expect 1 over r to the d, 1 over r cubed in 3 dimensions, like on the cubic lattice, or 1 over r square on the square lattice, for example. There's a little wrinkle which I'll come to later, but this is essentially correct. Extending this idea, monomers, which is vertices that are left untouched by a dimer, which are not part of the fully packed set of configurations, but you can introduce them as test objects. They behave like plus or minus 1 charges depending on whether you put them on the A sublattice or the B sublattice. So if the E sublattice side is left free, not touched by a dimer, that's like a plus 1 charge, and the B sublattice side correspondingly is a minus 1 charge. You can also think in terms of test anti-monomers, where 2 dimers touch at a point, and they will behave like a minus 1 charge on the A sublattice and a plus 1 charge on the B sublattice, just in this picture of polarization fields. And in either way, either you look at the test monomer anti-monomer pair on the same sublattice, or a monomer pair on opposite sublattices. By this electrostatics analogy, you expect they interact via Coulomb potential, and going like this. So 1 over r in 3 dimensions, log r in 2 dimensions, and so then you expect that the correlation function of test monomers will be of this form. So specifically in 2 dimensions, which is the case I'm going to consider, all this can be rewritten more simply. So the polarization field is just the transverse gradient of a scalar height. The effective action is just a Gaussian field, free Gaussian field. And this potential between 2 monomers is just G log R. Now the coefficient becomes important. And so the test monomer correlators are 1 over r to the G. And for non-interacting dimers on square and honeycomb lattices, from the exact solution of Castellan and Fisher, we know G is half. So this is sort of my lightning review of bipartite dimer models on square and honeycomb lattices at the very least. Non-bipartite dimer models, by which I mean fully packed dimer configurations on, let's say, the triangular lattice or the Kagome lattice, which would be the prototypical examples in 2 dimensions, they are very different because there's no way you can write a description in terms of some divergence repolarization field, because that really relies on this notion of an arrow going from A to B, and there's no A-B sort of property for vertices on a non-bipartite lattice. And the test monomer-antimonomer pair then has no long-range interactions and is quote-unquote deconfined. So they're really very different. Dimer correlators are very short range and so on. So this was the primer. Now I come to what I mean by the monomer walk. This is just a way of describing the standard worm algorithm a lot of us use in doing Monte Carlo simulations of such dimer models. And let me describe how it goes. So you land at the 0th step at a random site of a fully packed configuration that you are trying to change with detail balance. You walk that initial site I'm calling the first entrance or E0. You walk from this end where you have landed to the other end of that dimer. That becomes your first pivot. And I call it a pivot because now the basic move is to try and rotate this dimer about this pivot so that it overlaps with this exit, this exit, this exit, or somewhere. And you do that with detailed balance, that step. That's step 1. Then at the next step, you've got some overlap like this. Then you go along the other dimer that pre-existed, let's say this one is this one, and walk along it to the next pivot and keep doing this. And each step you carry out with detailed balance. And if you carry out each step with detailed balance, in the end you can accept the new configuration generated with probability 1 and know that you are doing an equilibrium simulation of your dimer model. What these detailed balance probabilities are for various exits depends on whether you have a non-interacting dimer model or you put some kind of interactions between them. But this is the general idea. And when I say you accept the new configuration, you get a legal new configuration only when this overlap site, which is the anti-monomer, moves around and then returns to the initial entrance and annihilates the monomer. And then you're back to the legal configuration space and you have a new configuration. So that's the monomer walk. Okay. So it has a flavor of a random walk, but somehow coupled to a background of dimers. And that is what I find interesting. So the question I'm going to ask in this talk is what is the return time distribution of this monomer walk? Okay. But before I tell you what we did with this, I should say why is this question interesting at all. So let me try and give you 2 or 3 reasons. So one reason might be, you see this worm head, so this overlap site I think of as the head of the worm, and this fixed entrance site which is now become a monomer is the tail of the worm. And there's this worm going around and it comes back and eats its own tail, right? So the head of the worm, as it moves, it keeps changing the background dimer configuration in a way that obeys detailed balance for this coupled system, right? And the Monte Carlo move ends when you return. So heuristically, this head of the worm is moving in the Coulomb potential of the tail. Because remember I told you a monomer and an antimonomer kind of attract with a Coulomb potential. So heuristically, you've got this random walker that's moving in a Coulomb potential. Okay? So how far is this picture valid? That's one question. There's another reason I can give. This thinking in terms of the head being attracted by the tail with the Coulomb potential leaves out another feature which is interesting. If I think about both the worm and the background dimer configuration, this is an explicitly Markovian dynamics. But if I kind of ignore or integrate out the dimers and I just look at what the worm is doing, the steps of the worm are going to be very correlated. The step a worm makes, the worm head makes now is going to be very correlated with the step it made at an earlier step in the walk. And that's because where the worm goes is dictated by the dimers it sees around it in some complicated way, which we write down with detailed balance. So the correlations of the dimers translate into history dependence of this worm head's motion. So there's history dependence due to the correlations of the underlying dimer configuration. And so this is of course only significant if the dimers are power law correlated, which they are in these bipartite dimers. So there's this history dependence, there's this Coulomb potential. These are the two sort of heuristic ideas for thinking about this. And there's yet another reason, I might add. There's many ways I can maintain detailed balance, right? It's not unique. The solution to the detailed balance equations is by no means unique. And so then the question is, whatever dynamics we get, whatever is the persistence property of the walk, is it universal across all these prescriptions and across bipartite lines? Is there universality? In some sense, this question becomes interesting only if there's universality, right? Because then there's likely to be some coarse-grained, nice description of this. Otherwise, it's going to depend on some details of your algorithm. So these are the reasons I can offer for wasting computer time on this. But having said that, let me tell you what we get. So before that, I should give you a little bit of background. So if you just had a regular random walker, right, none of this stuff, without any potential, nothing, no central potential, then we know in 2 dimensions you have this return time distribution, which is basically 1 over tau, but with some log square correction. If you have a log potential of this form, we know that you have a power law return time distribution where this return time exponent theta, persistence exponent theta, is just half the coefficient in front of the log. Right? For example, you can get this from Bray's paper in 2000. I'll give you one last piece of background. If you wanted to look for this numerically and didn't know these results, these exact analytical results, but wanted to see this in a simulation done in some L by L box with periodic boundary conditions, let's say, I would need to account for the finite size of my simulation. So the natural sort of expectation or postulation for finite size scaling form might look something like this. You would say P of tau is 1 over L to the power z into 1 plus theta times some scaling function of tau over L to the power z, where z is of course 2 for the regular random walker. But otherwise it's the inverse of the Hurst exponent h if you have some fractional Brownian motion. I mean, you might just postulate this kind of scaling form on general grounds, and C and D would be some microscopic parameters, order 1 length scales and time scales that depend on the lattice, but this should be a universal function. So you might think this is the right way to think if you're looking at simulation results. Now actually we just wrote this down, but if there's any literature on what's the correct finite size scaling form, I would really love to know. I don't know the answer. So now let us go to our results in the remaining 10 minutes, 5 minutes?
Yeah, 10 minutes.
10 minutes, yeah. Okay, very good. Perfect. So first, I'm on a L by L lattice with periodic boundary conditions. So the worm head can wind around before it eats its tail, right? So I can split every worm into whether or not it's a winding worm or a non-winding worm. I have 2 populations in the course of my Monte Carlo simulation. I should also add that the way we do this is we do many Monte Carlo steps using the same worm algorithm and then measure the properties of just one worm. So that we are always starting with an equilibrium initial condition. And then again do many Monte Carlo steps and then measure the properties of the next one, like that. And then this is the histogram of return times of the worms we measured. And I'm only looking at non-winding worms right now. And I see what looks like a nice power law with some cut here, which depends on the finite size I'm in. Different sizes get cut off at different places. And by studying this, I should get Z, right? So the power gives me the theta, and we get this number. And now I try to scale, and I should add and emphasize that this is done for the honeycomb lattice and the square lattice, and in both cases for 2 different versions of the detailed balance that I impose. 2 different solutions to the detailed balance equation. So there are 2 algorithms, 2 lattices, and I can scale everything by some non-universal numbers C and D here for the honeycomb lattice. Square is kept at 1 by convention. Exactly this postulated scaling form works. And this is done of course by adjusting Z so that it collapses. And we find this exponent. So I can do the same thing for the worms that wound round. right? Which is of course a much rarer thing, but because I can separately study them, I can actually look at these rare events quite easily, although these numbers look fantastic and hard to believe. I've just got two different populations, so you shouldn't worry about how I got this, because once you have a winding worm, you can just look at it. So again, two different algorithms, two different lattices. All of them have these sort of bell-shaped curves on a log-log plot, but I scale exactly in the same way. And okay, so there's some error, of course, in the choice of scaling parameters. We just do this visually, what seems to fit best, and then the spread around it. So this is the basic result on bipartite lattices. So my question to this audience is this fractional Brownian motion? I mean, Z is not 2, and there is history dependence, right? And this goes back, like I said, to some earlier work we did on some very complicated worm algorithms for frustrated icing models, where we couldn't think in these simple terms because the algorithm itself was very, very complicated. That was part of Geeth's thesis. So I'm going to leave the audience with this question for this part of the talk. Is this fractional Brownian motion? What should I do to confirm this better numerically? Or what should one do next if I wanted to really go and stick my neck out and say this is fractional Brownian motion? Clearly there is history dependence, so it's not unreasonable to think in terms of fractional Brownian motion. I mean, each step is correlated with the steps, many steps backwards in a power law manner. So wait, so H is, so I need to know what is H, right? Sorry? No, but what about this potential? If this picture is true, I'm thinking of a fractional Brownian motion in a log potential, roughly. Right? So I don't know what else to check. Maybe I should look at some correlations between steps explicitly or something. I don't know. So this is so far as we have got. And I'm just writing on a slide what I just said. Why do I want to even ask this question? Because of this. But here's the point. In my mind, at least, the history dependence is controlled by the dimer-dimer correlations. Because after all, at every step, it looks at the dimers around it and makes a step, right? And if the dimers are power law correlated in space, that means the worm's motion is power law correlated in time, in some way, right? So the history dependence is controlled by the dimer-dimer correlations. But this sort of potential between the head and the tail of the worm is actually exactly controlled by the monomer correlators, monomer anti-monomer. Right? So there's two different aspects to this critical dimer model that somehow contribute two different things. So very crudely, I would say Z is controlled by the dimer correlation exponent, and for a fixed Z, theta can change if the monomer correlation exponent changes. Right? That is the picture. So now if I want to test this, I should try and find other examples where the dimer correlators are different. I can do that by adding interactions to the dimer model. Fabia is an expert on that. But the problem with that is, on a bipartite dimer model like the square lattice, you add interactions, both the dimer and the monomer exponents change in this way. The stiffness changes, and eta m, the monomer exponent, is linear in G, and eta d is 1 over eta m. That's just the way it is for this Gaussian field theory. So you can't keep this fixed and change that. So that brings us to sort of the last idea in this talk, which is, I'll just put this here. So you take this decorated honeycomb lattice or star lattice, depending on what you like to call it. It's one of the Archimedean lattices, by which I mean all the vertices are equivalent to each other, but all the bonds are not. Right? There are kind of bonds that are inside triangles and bonds that are connecting triangles. It's one of the 11 Archimedean lattices, but so all the vertices have to be the same, but not the bonds. Now, it's not hard to argue, and I won't do that here. This observation I'm making here is what started us on this part of the project. There's a statement I can make which is very easy to see, that if I take the fugacities of the dimers to be 1 on all these intertriangle bonds and T on the triangle bonds, then this is exactly dual to the triangular lattice icing model. And likewise, if I take one unit to be 2 triangles connected by a vertical line and give all of them fugacity 1 and the other bonds fugacity T, different parameterization, this is dual to the square lattice icing model. You can just see this. And, I was just asking Deepak is this the 400th way of solving the 2D Ising model? Because, I don't think there's anything exactly like this in the literature. We found some close relatives. So if anybody knows more references which do something like this, I would be very interested. But anyway, the point here is not to say you solved the 2D Ising model. The point here is the dimer correlator is mapped to the bond energy correlator of the Ising model. So eta d remains 2. But there is no height theory. There's no reason to expect that the monomer correlator is 1 over the dimer correlator. So this is exactly an example I'm looking for, where I can keep the dimer correlators fixed and the monomer correlator will be something else, and then I can look at the return time distribution. Right? So that's the idea. And so first we need to know what is the monomer correlator. So that we measure ourselves numerically, and we get a pretty good fit to 0.24, very different from half, right? So this is for the triangular lattice Ising model critical point. That is the star lattice dimer model in this parametrization. And this is for the square lattice Ising critical point, which is the star lattice dimer model in this other parametrization. Right? In both cases, you have the same eta m. And eta d is by construction just 2 because it's the energy correlators of the Ising model at criticality. This is all at criticality. So the point is we know from this mapping at what t in each case you have the critical point, and we go there. Brings me to the final statement here. So now I look at the return time distribution, and I seem to get a very different slope. So theta, the persistence exponent, is very different now. It's not 0.35, it's more like 0.25. And it scales nicely. So the scaling ansatz works, and from the scaling ansatz, the fit, I get Z, and it's the same as I expected from this heuristic. Because the dimer correlators have not changed, I don't expect Z to change because the history dependence has not changed. So within errors, the history dependence is, the dimer correlators have not changed. So within errors, the dynamical exponent is the same as in the bipartite case, but now my persistence exponent is completely different. And the same thing happens in the star lattice, in the square parametrization. Again, we find the persistence exponent changing, but Z remaining the same. So this heuristic seems to work. That's the basic conclusion. And so this really leads me to suspect this is something like Brownian motion, but I don't know how to, quote unquote, prove it numerically. And let me stop here. Thank you.
Long live India and France friendship.